Hi, and welcome to this post-lunch session. I hope that I will be able to keep you awake after lunch. So this session is called Stop Adversaries Ahead, using AI in adversarial settings. Look at these two images. While for the human intelligence engine, aka our brain, they look totally identical. For the AI engine, it sees something completely different in both of them. While in the left image, it sees it can make a good separation of the cars from the trees, from the road. In the right image, what the AI engine sees is a large minion standing in front of the camera of the vehicle and just waving his hands. And this is not at all surprising, because this image was generated exactly for this objective, to try to deceive, to fool this semantic segmentation AI that analyzes this image. Before diving into the outline of this conversation, let me start with why I think this session is important. It is important because I think the threat of AI deception, sometimes called adversarial examples, is an area that is very important. It presents an acute and immediate threats to many systems, to many AI solutions, and probably to at least some of you or most of you that design AI. What is included in this session? I'll start with what is AI. I try to answer the questions like, what is AI deception? Why does it happen? When does it happen? Should we care about it? And what can we do about it? A couple of words about myself. I'm Itsik Mantin. I'm lead scientist at Imperva. The last 20 years, I've been innovating in security algorithms and in their intersection in many different domains, in cybersecurity, cryptography, DRM, vehicle security, and others. I have 20 patents in these areas. And my main focus in the last couple of years is how to take these leaps forward in AI and machine learning and bring it to our world of cybersecurity, to incorporate these models and to make better security solutions in our world. In my free time, I do anything that can be done outdoors, not in the office, hiking, biking, trail running, or just visiting exotic places. I'll start with very unique example. I think it was almost 2 years ago, I saw this article saying that Volvo admitted that their self-driving cars were confused by kangaroos while they were doing a pilot in Australia. And the question was, why did that happen? So it seems that the AI is looking at the distance of objects from the ground, which is essentially static in many cases, in order to observe, to analyze the size of the object, or the distance of, or the exact location of this object. However, when it comes to kangaroo with this intensive vertical motion, it seems that it is something that this AI never seen, which broke this latent assumption that AI models do, that the future will essentially look like the past, which means that the model is as good as the data that it gets. So since this car before that probably had hundreds of thousands of driving hours total in different countries, it probably never been to Australia, and it never saw a kangaroo or other objects with such vertical motion, which means that this vertical motion presents some kind of an edge case for this AI. It means that it falls in the 0.0001% of the blind spot of this algorithm. And even more concerning, that this problem was not done intentionally by the kangaroo. It just was there. So what can do an attacker in these circumstances can be even more concerning. So let's look at this idea of blind spot or edge cases from the perspective of an attacker. So there is very significant difference in the way attackers and builders think. when you build a system, you think about different components. You assume that everything goes as planned. You are considering, of course, a couple of irregularities in the inputs, and because you know that it can happen from time to time, and you want the system to continue working in the presence of this. But when it comes to an attacker, it actually looks for the edge cases. What happens? What does the system do when it gets abnormal inputs? Usually, an attack does not start with, oh, this is a vulnerability. It starts with, hey, this is odd. This shouldn't happen now. And when it comes to a system that fails in very, very rare coincidence, then in some cases, the builder can say, OK, that's good enough. This is a probability that I can live with. But when attacker looks at that, then he says, oh, this is something I can abuse. And then the builder is happy, but also the attacker is happy. And the reason he's happy, because whenever you say rare coincidence, you implicitly say probability. When you say probability, you say there is some dice that someone throws and can fall on 1-1 or 1-2 or 6-6, and you might get lucky and you might get not lucky. However, when the attacker has control over the input, then there is no real dice here. You can just put the dice on the exact numbers that he'd like. And to do a paraphrase on Albert Einstein saying, maybe God does not play dice, but the devil definitely does. In the security world, we have this axiom which was proven time after time after time, which is when a new technology is being developed, being designed, without thinking about the possibility of someone trying to break it, the possibility of having an adversary in the area, then when this adversary will arrive, and it will fail, and it will usually fail bad. That was the case for the internet. It is the case for today for smart cities and IoT, and for this Corkinet that you have now in Tel Aviv that were just recently hacked, and all kind of systems. If we go back now to this example of the kangaroo, then an attacker that identifies that there is this blind spot of this AI with this vertical motion can come to the middle of Manhattan, to a car that he wants to deceive for any reason, and then to generate artificially this very odd and unique situations, which probably this AI never seen. Now, I don't know what will be the outcome of what the AI will think when it sees this kind of scenes. But it is very likely that also the designers of this AI, when they created it and when they tested it, they still may not be able to tell what exactly will happen. And again, so again, this is an edge case, and this is something that is a lead to start an attack from. The first examples, and probably the most famous examples of adversarial examples, were presented by Google in 2015. When they took images of a panda, and they added some human invisible noise to it, and then the visual object recognition classified this as a gibbon, and they do the same for a bus, and it convinced the AI that this is an image of an ostrich, and all these images in the right side actually are classified by AI with very, very high confidence as ostriches. So we saw at the beginning this minion with the semantic segmentation. So semantic segmentation is vulnerable, and now visual object recognition is also vulnerable. 2 years ago, a research by Bar-Ilan University and Facebook, they created a framework they called Houdini, which was designed exactly to do that. The example of the minion came from this research. And they did the same for pose estimation AI. And then the image that you see in the top right is a variant of the image in the top left, which adds an invisible noise. And now the AI that tries to understand the pose of the body sees someone lying instead of someone standing, and vice versa. So pose estimation is also vulnerable, and they did the same also for speech recognition software. And essentially, as I said, in most of the cases, if you don't build a system thinking about an adversary, then the effort that is required in order to deceive it is usually not as significant as you may think. So this area attracts quite significant attention in the academy in the recent 2 or 3 years. However, in the industry, I don't see this attention. I hear things like, sayings like, this threat is theoretic. My system learns all the time, so adversarial examples are usually non-persistent. They happen to just a single image, so it is not an issue. This is a problem of deep learning, but we do ML, no problem. We use ensembles, so it is much safer. But why would anyone want to do that? And there are other ways that the attacker can get the same impact. But all of these are things that I'll answer some of this in this slide and some of this later. So regarding whether this is real or theoretic, then a stop sign that with some small patches that are insignificant for the human observer, which cause an autonomous car to think that this is not a stop sign but a speed limit sign, this is a real threat. This is not theoretic. And regarding the persistency, then what you see in the right side, there is these small patches on traffic signs and the success rate of the attack from different angles and different distances. So, which means that these examples, these attacks becomes more and more persistent. And what we love to say in the security and cryptography area where I come from is that attacks never get weaker; they only get stronger. So from that point on, situation will only get worse. Another example for face detection system. So what you see in the right is these colorful glasses, which were proven to fail face detection system. Also these face colors, and this very unique hat that you put at it, and it projects infrared light on your face, which will fail face detection systems. So you can fool by that any kind of surveillance system, either whether it is Big Brother system or just what you have in the airports to stop bad people from passing undetected. And another super cool example, which I saw 2 years ago in a security conference, which was a bot versus bot research. Super cool. And what the attacker did, they wanted to evade an antivirus that was designed using machine learning. And what they did, they built a library of neutral code transformations, which is, an exercise that, a third-year student of computer science can probably do, just to create transformations that change the code without changing its functions. And then once they have this database of same essence, different look code snippets, then they relied on the assumption that this AI has some success rate. Maybe one time in 100 million it will fail, and the rest it will succeed. And now, once they have this AI within their lab, now they can try just to launch all these samples and to see how they are blocked one after one after one, until they found this edge case, this blind spot of the algorithm. And then now they have this special crafted code snippet that does the malicious functionality, but it goes under the radar of this AI. At this point, they just go to the field and they use this sample and they win. No dice, no random bits, just win. So let's, if we continue to speculate about where can be the risks and of AI systems. So usually most of the examples that we see are coming from from image processing and video processing and speech recognition. But actually any kind of AI that does any kind of algorithms actually can be vulnerable to these kind of attacks. You can think of a recommendation engine. So there's always this content provider that wants to promote his content, and what he will do for that, he will use fake transactions by dummy users, aka bots. If you have an AI that does algo trading, then trader will want to promote a stock that you just purchased. You can do this by creating 2 or 3 abnormal transactions of just buying one stock with 5x value, which might be exactly something that the AI looks for in order to identify that the stock is going to go up. In the case of visual object recognition, we talked about that. There's this face detection software and minions and ostriches and all sort of stuff. When it comes to autonomous cars, there is not only the analysis of the scene. This scene, eventually, this image of the scene is being translated into a perception of how the worlds look like at this point. Now it goes into a second AI that thinks what is the right action to do. Should we pull the brakes? Should we pull the gas? Should we steer right or left? Now think of a bad guy. This is completely hypothetical exercise, okay? That he just presents a doll, a girl that looked like a girl, and put it in front of the car, of an autonomous car, in a distance that the car has no chance physically to stop in time, and it does that in this road. Now, what will happen? Will the car decide to go into this girl? Or will it just do some very strong, aggressive steering to the right or to the left? I don't know. But if the designers of the system didn't think of the situation, then very, very odd things can happen. Here are some, I'm not sure how exactly to activate this. I want to just, oops. Just a second. I want to just click on this video. Okay, these are some examples of things that were recorded by Google cars, autonomous cars. They are things that they've seen. So a lot of very, very odd situations can happen. So you can say, okay, so Google cars, when they were around, they saw a lot of odd things, so maybe they learned them. Maybe they did, maybe not. I can hardly think about something that captures all the different things that an adversary can think of or do. And to make things even more complicated, a research on transferability of adversarial samples. Usually, in our world of data science, when you talk about transferability, we talk about taking one model to work in another, to solve another problem. But here, transferability goes against us. They analyzed the case where there is a model, a classification model X, that has a pretty good success ratio on normal samples. And then the bad guy, the adversary, comes and he generates some deceptive samples that are able to fail this model. Now, suppose that there is a model Y that someone else built independently, okay? It turns out that the transferability works, that in many, many cases, the samples that were generated to deceive model X are also effective against model Y. And this essentially kills mitigation solutions that suggest to say let's obfuscate the model, and then we're good, we're done. So, what can we do about it? So before getting into the mitigation toolbox, I want to sync up expectations. In this conference in Bar-Ilan that focused on this area, I think the main conclusion that there is no silver bullet. There is no one single approach that once you use it, this threat is completely eliminated. What you have is a collection of different mitigations nuggets that you can use. In some cases, they will be more effective. In other cases, they will be less effective. And they are usually very specific to the usage, to your usage. So when you come to a system and you want to make sure it is secure, then there is a very strict and rigorous process that security architects do. You first have to think about who is the attacker. Is there an attacker? Is there anyone, an entity, a stakeholder entity within this environment that wants to do our system to do something it is not supposed to, which is the threat? And once this is the case, do we even care? Maybe they want to do something that we don't care about. If we have a threat, then we go to security analysis. And we try to think about whether these attackers, these potential attackers, what are the different ways they can implement, they can realize this threat. In our case, can the attacker influence the input to the AI? Can he do it directly or implicitly? How easy would it be? Should he just penetrate an organization in order to do that, to be an insider, or can he do it from his couch at home by sending a web request? Can they observe the decisions of the AI? Most of the attacks I talked about, they work in a black box model, where the attacker does not know the internals of the model. all he sees, all he has is he has access to the black box that say, this is a dog, this is a cat, this is a dog, this is a cat. And that was sufficient. So can the attacker observe these decisions of the AI? Assuming that we understand that there are situations, there are threats that can be realized in our system, then we have to analyze the model. Is our model robust enough? Which means that, is it possible that by doing small perturbations of the input that are insignificant to the essence of the model, like changing a couple of pixels that keep the image the same for a human eye, but change the decision of the algorithm, whether it is a cat or a dog? And assuming that we understand there is a problem, then we go to the mitigation toolbox, which is the next slide. So we can divide the mitigation into 3 different classes or categories. The first type is in the data area, based on processing of the data before it is entering the model. The second is in the selection of the AI model itself. I will dive in each of these categories later. And the third is, in some sense, the AI architecture, the usage of the AI. It's choosing the correct AI task, giving it the right input, or doing different things with the decisions that the AI makes. So when it comes to the model selection, so we can prefer to use models that are more robust, which of course will by definition be less vulnerable to these small perturbations. Explainability is a very important feature here, and the reason for that is that assuming that you have a model that is not explainable, you have, the model is a black box, just say cat or dog, then once you are a victim to an AI deception attack, and you even suspect that, you don't have any way to do forensics, to try to understand what has happened here. What you see is just something that looked bad, and you don't have any way to proceed to do anything from that point on. And the third one in the model area is to prefer, at least in cybersecurity applications, to use anomaly detection. In security, you have essentially 2 models, 2 approaches. You have negative security model, which says what is bad, anything else is good, which is by definition fairly easy to evade, because if you just deviate slightly from these rules, from the signatures, then you are in a different area. And there is this positive security model, which says what is good, anything else is bad, which is, in machine learning, it is called anomaly detection, which is by definition more robust. When it comes to the processing of the data, then first you want to clean all the data that you are using for the training, because it is possible that the attacker polluted this data, and then you are building your model is as good as the data that it gets. And there are several approaches for data regularization or validation, meaning that you do some filtering to the data before you enter it to the model. You want to make sure, for example, in this example of the ostrich, then you can do compression for the image, and then the compression will throw away this high frequencies from the image, and then probably with this noise. Autoencoders were discussed in several places. At some point, it was believed to be the silver bullet to solve this problem, but eventually it is not. It makes the life of the attacker harder, but not impossible. So input validation, to validate the input is natural, is not anomalous, and such filtering are, to some extent, they are effective against this threat. In the usage area, then there are many things that you can do. You can avoid raw inputs, which gives less influence of the attacker on the inputs. You can choose tasks for the AI that the adversary does not care about, like generate insights. You can hide the decisions of the AI to prevent these black box attacks. Transparency is related to the explainability, which I talked about. And you can just do fault tolerance. You take this decision of the AI and to combine it with other mechanisms, like a rule-based, to make a more correct decision. I will end with an example of how something that we did in Imperva. We wanted to generate, to identify attacks in database access logs. And at the beginning, we thought about, OK, let's take the logs, do anomaly detection, and then we win. But essentially, we reached the conclusion that this approach, well, everything that we do, we are a cybersecurity company. Everything that we do, we have an attacker in mind. So we thought that this is, of course, can be vulnerable to these attacks. And it also creates many false positives. So what we did is we created an intermediate layer that we call data intelligence. And there we we put a lot of machine learning models that they don't try to detect attacks. They try to see within the data, what is it that we are seeing. We try to understand who are the users, what are their types, which are database admins, which user accounts are being used by machines, by application, understand the networks and the database. And what we did based on that, we created a high-level language on which we could use now for very simple attack patterns, like user of type X should not access data of type Y. Based on that, we also build a baseline model for what is typical within this system and run anomaly detection over it. So I don't have time. So I won't get into exactly how this fulfills all these security mitigations, but let me just summarize. So I hope I answered these questions. And to summarize, so AI is an awesome technology. It tends to fail bad in adversarial settings. AI deception has a variety of mitigation approaches, but there is no single silver bullet. And safe usage of AI in adversarial settings is usually possible, but it mandates security thinking, AKA an ostriching. So don't ostrich yourself. And thank you very much for